Mhm. Hi, Srudu. How are you? Can you hear me?
Hi, Nafisa. Yes, I can hear you. Hi,
It
everyone.
looks like I've just woken from an afternoon nap.
No. I was at home. I was at
Oh,
home. Let's start the
I have
meeting.
just woken from my
Let's
nap.
start the meeting in 2 or 3 minutes. Let me just get some coffee and let's start.
Yeah, no problem. No problem.
Is any? Do you
Uh,
think anybody else is going to join or? Um,
I don't know.
okay, no problem.
Guys, all of you who have joined, please
Yeah.
mention on the
Okay.
group that we are beginning in 2-3 minutes. So if others want to join, they can join.
Okay. Okay, Saurabh. I think he has a mic problem, but yeah, no problem. We'll start in a minute, 1 or 2 minutes.
Oh my God.
Okay, great. I think we can start right now. Can you hear me?
Yeah, let's begin.
Okay. Uh, so today we'll be talking about tests of association for continuous variables. So t-tests and ANOVAs. Last time we talked about, this was 1 week ago. So I think more than 1 week ago. We talked about chi-square tests. We talked about Fisher's exact test. We talked about basic statistics. We talked about what statistical test we are going to use or what type of data. So in this video, in the last series, let me just recap what we did. We had both of our variables, the dependent and independent variables, were categorical, and then we saw when we will use a chi-square test, when we'll use a Fisher's exact test, and when we'll use the Yates continuity correction. So to recap, when both of our variables are categorical, and if we plot a 2x2 contingency table or even a 3x3 contingency table or so on and so forth, if any one of the cells includes 0, we will use the Yates continuity correction. So chi-square test with continuity correction. If any of our cells in a 2x2 contingency table is less than 5, we will use the Fisher's exact test, or even for small sample sizes, less than 50 typically. So that is when we'll use the Fisher's exact test. So last time, I asked every one of you to go back and play around with JASP. So have you done that?
I did play around with it. I have like, what is OSF? Then I went into deep into that whole
Yeah.
open science framework. Like, do you use that?
The OSF, no, not that much, but I have you experimented with that?
I was just searching about it.
Yeah.
Gonna make the so for records and sharing it, it's not. We don't have electronic records, no, so I don't think that's really useful for us.
Yeah. So it's when you want to collaborate. So OSF is when you want to collaborate on data sets or analyses. So you use that then. So Stark Potato, who's Stark Potato? Is it Saurabh?
Yes, boss.
Yeah. So,
It was very here the schedule is very horrible. means means every week we had examination, so I looked a bit, but couldn't spend much time on it, unfortunately.
yeah. Okay, so let's, I think, start with this. Let me share my screen. Okay, so I want every one of you to open JASP. So I hope last time people you were using, some were using JASP on their PC, some were using JASP online. Have you downloaded JASP this time?
Yep.
Okay.
The web version was horrible, man. I lost interest in it.
Yeah. Yeah, the web version is, I don't know. I honestly don't know who uses the web version.
I wasn't able to download, man, and then I wasn't able to download it at all, like for 3 times, and then I did a USB tethering with my phone, and then I was able to download it.
Yeah.
I don't have a Wi-Fi, no, at my hostel. So.
Yeah. Okay. So I think, so let us start with, so last time, I see some new people today. So welcome everyone. And today we'll be talking about t-tests, ANOVA. So those are the parametric tests we'll be talking about, and the Wilcoxon ranked sum, also known as the Mann-Whitney test, which is analogous to the t-test, and the Kruskal-Wallis test, which is analogous to the ANOVA. So we'll be talking about both of these tests as well. So these are non-parametric tests. So I want you all to So for the new ones, I want you all in JASP to go to the show main menu option. So there are 3 horizontal stacked lines, the top left corner of the screen. So should I give everyone a moment to, load JASP, or is everyone okay to go?
Yeah, we are okay to go. Is
Okay.
there anyone like our new members? Do you need time to download Jazz? But still, it would take time. Just follow the instructions on screen. We have a recording as well, and then you can practice on later. You can put the Jazz on download if you haven't already. Yeah.
Yeah. So I think so. I want everyone to go to this show main menu option and go to open, right? So show main menu, open, go to data library. In data library, I want you all to go to t-tests. So t-tests and open the directed reading activities, the JASP file. So remember that there are 2 files in JASP. So one is the JASP file, which contains the analyses, and one is just the a simple data file. So I want everyone to open the JASP file so that we get a description of the data set itself. So just to quickly recap for the newer members, so there are 3 panes essentially in JASP. So this is the middle pane, this is the right pane, and when you click this small triangle show data, you will get the data viewer pane. So there are 3 panes in JASP. There are 3 panes in JASP. This is the data viewer. This is where you will change the settings for your tests, and this is where you will get your output. So analyses and tables, figures, and you can even annotate your results. So before we read the description here, we'll just have a look at the data set before reading the description. So ID seems to be, of course, the identification variable. Group seems to be, there seems to be 2 groups, so treatment and control. And so G, so this has been coded. So the group has been coded 0 or 1. And DRP seems to be some sort of continuous variable. So just to recap, in JASP, there are 3 types of variables: scale variable, also continuous variable, also numerical variables. Ordinal variable, so this is the icon. So ascending to descending or descending to ascending. So small to high, high to low, right? So ordered, ordinal, and nominal. So norm, name, right? So these are names or labels. So the 3, small circles in a Venn diagram sort of shape in JASP. So this stands for nominal. So this is a scale variable or numerical variable. So these seem to be some sort of, numerical values. So now let's see what this data set is about. Okay. So this data set is labeled directed reading activities. And this provides the reading performance of 2 groups of students. So one control group and one which was given. So one group which was not trained, and one group which was trained, who were given this activity, right? Directed reading activity. And then the reading performance is measured. So the reading performance is the DRP variable. So the performance on degree of reading power test, right? So this DRP variable is the degree of reading power test. Group and G are the same thing. They are coded, right? So 0 for the treatment group and 1 for the control group. So this is the coded variable. Group is again the same variable, and ID is the identification number of a pupil, right? So now I don't want everyone to go and see the analyses. I want everyone to remove the analyses. So we'll start doing the analyses ourselves from start. All right. So if you all remember, before setting out to do any analysis, we would of course first like to do some exploratory or descriptive analyses. So descriptives, to summarize what descriptives are for the new viewers, descriptives are summary statistics. So what are summary statistics? Summary statistics are means or averages, standard deviations, medians, interquartile ranges. So broadly, descriptive statistics can be divided into two. So measures of central tendency and measures of dispersion. So if you analyze the names themselves, what do measures of central tendency mean? So measures, of course, are some value, right? Measure means a value, and central tendency means, so if you have a data set of 100 patients, say for example, so measure of central tendency is what is the center value, right? So what are the central values? So measures of central tendency include means, medians, and modes. So mean, of course, is the average, right? So for example, consider this degree of reading power test score. So how many students do we have? 44. So the measures of central tendency for DRP will include means, medians, modes. So what is the average? So you add all of these values and you divide all of them by the number of samples. So in this case, the number of samples is 44. So you add all of these values and divide by 44. That will give you the mean. What is the median? So median is when you arrange all of these values from smallest to largest. So for example, say 24 is going to be a small value 17. So we can also do this, in JASP itself by this label. This should be possible here. And probably order. For some reason, my version of JASP. Okay, yeah. So now it is ordered, right? So from the filter menu. So the least value is a score of 10, while the maximum value seems to be score of 85. It seems 85. So when you order it from the least to largest, the middle value which you get from all of the ordered values is the median. And the mode is the value which occurs the most frequently. So now measures of dispersion. So what does the name suggest? Measure again value. And dispersion, right? If you imagine what dispersion means, it is how far the data are spread. How far data are spread. So how far the values are spread. So for example, I'll give you a very simple example to clarify this. Say we just have a sample of 10. Okay, for example, we have a sample of 10. We measure the systolic blood pressure. Okay, so 10 systolic blood pressures in 10 different people. And we get values of SBPs of 120, 121, 119, 120, 122, 118, 120, 119, 121. So all of these are pretty close to each other, right? So just, a difference of 1. So they are very close to one another. So the dispersion between all of these values is pretty small. If you consider the same measurements, so 120, 114, 126, 132, 108, 100, 140. So these values are dispersed, right? So any measure of dispersion will be quite large. So for example, the standard deviation will be large, the interquartile range will be large, so on and so forth. So this is what we mean by a measure of central tendency and a measure of dispersion. So essentially, when you are reporting your descriptive statistics, you should always report the measure of central tendency for your data and a measure of dispersion. So for continuous variable, you would want to report either the mean and standard deviation, or the mean and standard error, or the median and interquartile range, or the median and the entire range, so lowest to largest, that can also be reported. And we'll see some other measures shortly. Now, how to do descriptives? The ones who were present last time will immediately know. But for the newcomers, so all of these are, if you open JASP, all of these which you see are modules. And if you see this drop down, your small downward pointing arrow, that means that you have more tests inside this module. For the purposes of this entire series, and I am pretty sure for the purposes of your own personal purposes, the classical version is more than enough. So classical or frequentist version. So Bayesian statistics employ completely different philosophy to approaching data. And if I were to explain it very simply, it would mean that you have a hypothesis before you analyze the data. So that is what we mean by prior. And so building on your prior hypothesis or prior measure, you perform some analysis on your current data, and then you compare that with your prior hypothesis, and then you compare and contrast. And so that is a very crude interpretation of Bayesian statistics. But we are very happy with classical statistics. We are very happy. This is also known as frequentist analysis. And this the classical version gives us our beloved p-values or probability values. Okay, so let's get straight into it. Go to descriptives. All right. And now we want the measure of central tendency and measure of dispersion for DRP. So DRP is the degree of reading power. These are scores, right? Numerical scores. And how do we get get statistics for this? You can select this variable here in this box. You can drag and drop it, or you can just select the variable and click this arrow icon, which indicates that you want to drop it into the variables box. All right. So this will give us descriptive statistics for the entire DRP group, but we want separate descriptives for both of our groups, right? So we don't want to compare the entire cohort. So because at its essence, both of the it is divided into two fundamentally distinct groups. So one group which has been treated with the direct training activities, and one group which is a control, who has not been trained. So overall, we can see that the average score which the student scored was 46, around 46, the standard deviation of 15. So I'm not going to go into the whole bell curve thing and how many standard deviation corresponds to how many % of values and etc. So that so this is a very practical session. So I'm not going to focus on that. Now we want to group our data, right? So fundamentally, we want to see whether there's a difference between the two groups. So you see this split box here, split. You can put your grouping variable. In this case, we can put either group or G. So both are the same, if you remember. So we can put either the group or the G variable here. Let me show you that putting either both of these will not make a difference. So both of these are still the same. But this 0 and 1 coding might not be very intuitive. So we'll just put the long form, control and treat. So it is easier for us to know which group is which. All right. So now immediately we can see. So what do we mean by valid values and what do we mean by missing values? First of all, so valid values are those which are not missing, or those values which are there in the data set, so which are present. And missing values, for example, if you don't have data for a certain variable for a certain person, so you can just keep that blank and it will show you, so for example 1 or 2. So those many cells you will have missing in your data, so it will give you those statistics as well. Now immediately we can see that the means for both of these groups is very different. So a difference of approximately 10. So a score of approximately 10. So those who were trained for reading scored 10 points better or 10 marks better than those who served as controls. So that is a measure of central tendency. And now standard deviation, you can see that, the control group, so their dispersion was a lot higher than in those in the treatment group. So if you think about it, so those who were, uniformly trained to, approach the test, their dispersion was not that high. And those who were, not trained, their dispersion was a bit higher. All right. So by itself, we can make sense of the data, but we need to formally test our hypothesis. So now we come to formulating our hypothesis. So this is our descriptive exploratory, descriptive analysis. And now we can formulate our hypothesis. So essentially, our hypothesis will be that there is a difference in the directed reading activity score between the treatment group and the control group. So there is a difference. So that is our two-sided or two-tailed alternative hypothesis, that there is a difference. Now, let me see who are present. Okay, Stark Potato, I want you to formulate a one-tailed alternative hypothesis, which is favoring the training group.
Okay. Just help me out. I will just show boss my screen. Give me a second. Screen. Post. You need to enable me, boss, for sharing my screen.
You can just speak this out loud. I will let you share your screen when I finish my session to ask you to show your analyses. Just formulate your hypothesis in a sentence. Your one-tailed alternative hypothesis.
Means regarding the null hypothesis, I can say that there was no difference in the reading speed in the control group and the treat group, which was trained for the reading.
Yes, that is correct. Yes. Yeah. Exactly. That's good. So the null hypothesis is perfect. I already mentioned the two-tailed hypothesis, right? So who would want to volunteer to reiterate the alternative hypothesis? Does anybody want to volunteer? Yeah. Okay. So Pratik has PM me. So everyone can PM me, right? So you can write your alternative hypotheses in the chat box and send a direct message to me, a private message to me. So Pratik, so what is this? Is this two-tailed? The mean score is different. Yes. Okay. Iman is correct. Yes. Yeah, correct. Pratik, that's good. Excellent. So that is correct. That is a one-tailed alternative hypothesis. So let me read aloud what Pratik has written. So does anybody else want to try? So Pratik has written, there is an increased reading performance indicated by an increased DRP in the treatment group as compared to the control group. So that is one-tailed in favor of the DRP group, in favor of the train group, or the reading performance, the treatment group, so treat group. That is correct. Okay. So now let me go further. And before I test this hypothesis, let me first show you what options we have in the descriptive statistics drop-down menu. Okay. So by default, JASP selects the valid, missing. So both of these options. So if you don't want this and you want to keep your table clean, you can deselect both of these. And I think it will take some time to reflect the changes. I don't know why my, oh, let me close my open tabs. Okay, so we can keep the table clean and we can remove the valid and missing check boxes. So here you can see that for central tendency, we have the median, which will give us the median. Even we can see that the median scores are also different. So by 11 points, that's a huge margin. And the mode. So the mode won't give us quite a lot of information. So you can see that the modes are 42 and 43. So, this doesn't give us a lot of information. So we'll just stick with the mean and median here for now. And here, standard deviation is by default selected. IQR stands for interquartile range. Variance is the square of the standard deviation. The range is the range of values from least, from least to the highest. So if you look at the control group, so the minimum value, the minimum score is 10 and the maximum score is 85. So the difference is 75 and that is reflected by the range. Even for this, 71 minus 24 is 47. So this just gives us a difference between the maximum to minimum. Okay, variance is the standard deviation squared. So if you, for example, 11. So 11 squared is 121, right? So this is a standard deviation squared. Interquartile range is the difference between the 75th percentile to the 25th percentile. Median is essentially the 50th percentile. Just a second. Okay, sorry about that. So now we can go to the quartiles option. If you see here, so the quartiles option will actually divide your data into the 25th, 50th, and 75th percentile. And if you carefully see, the median and the 50th percentile are actually the same, right? So if you think about what the median stands for, it is, the center value when you arrange your data from the least to the most. The 25th percentile is the 25th value when you arrange your data from least to the highest, and your 75th percentile correspondingly is the 75th value from when you arrange your data from least to highest. If you want to customize your percentile, so for example, if you want quintiles, so quartiles are 3, quintiles are divided into 4 equal groups, 5 equal groups. So for example, you can say 20, 40, 60, and 80. Then it will divide into 5 equal groups. So 0 to 20 is one group, 20 to 40 second, 40 to 60 third, 60 to 80 fourth, and 80 to 100 fifth. So 5 groups, so quintile. So you can get, essentially any customized percentile value. So for example, if you want 33, 66, right? So if you divide into into 3 equal groups, so you get your 33rd and 66th percentile as well. So you can play around with this, and if you want to evenly break the Okay, so you can essentially customize your percentile values by using this, and you just keep a space between two values. So for example, 33rd to 66, just keep a space between both these values. All right, now in distribution, so I won't go into the MAD robust coefficient of variation and all of these options. I won't go into skewness and kurtosis right now, but I will go into the Shapiro-Wilk test and sum. So essentially, there are certain assumptions. So if you remember, before performing any hypothesis testing, before performing any statistical test, you need to verify that your assumptions. So there are certain assumptions before performing a test. So those assumptions should be met. So one of the assumptions usually which needs to be met for parametric tests includes the assumption of normality. So what do we mean by normality? If you think about what normality means, what does normal data mean? If you go back to your community medicine lectures, there is a standard bell-shaped curve. It is normal, right? So that is what we mean by normal data. So the mean, median, mode fall exactly in the center of the data set, all right? And you get a nice, smooth, symmetric bell-shaped curve. So that is what we mean by a normal data set. What do non-normal data sets mean? So non-normal data sets are skewed. So those are skewed. They can be positively skewed or negatively skewed. Positively skewed data sets have their tails to the right. So larger values, so the tail lies to the right, essentially. So instead of explaining, let me show you what positively and negatively skewed data sets look like. Essentially, the Shapiro-Wilk test is a test for normality. So if you want to check the assumption, if you want to test the assumption, you need to perform your Shapiro-Wilk test. The sum is essentially the sum of all the numbers. So if you want to add 22, from 24 to 85, all of these values, so that will give you your sum for the control and treatment group separately this time. Okay. So let's come to the Shapiro-Wilk test when you perform our t-test. So this is how we perform descriptive statistics. So now, if you go to basic plots, select this distribution plots checkbox. It will give you a histogram of how your data is spread. And here is where I can explain what we mean by skewed data. if you select the display density, it will give you a nice curve. Okay. So if we have a positive, if you have a normal data set, it should look symmetrical. So this is quite symmetrical, right? Even this is quite symmetrical. So it is very symmetric to the left side of the central value, and it is almost equally symmetric to the right side of the central value. If we have a positively skewed data set, then the data, it will climb very fast. The central value will be very early on, and then the tail will be quite, prolonged like this. It will be quite prominent. The tail will be quite prominent, and it will be to the right. So this curve will rise quite steeply in the beginning and then fall very gradually. So the tail will be quite long. So that is a positively skewed data set. And the negatively skewed data set is the mirror opposite of that. So the tail, so the initial values will be, quite gradual, very gradual slope. And then the fall will be quite steep after that. So that is a negatively skewed data set. So when I ask people to perform analyses by yourselves, okay, we will use different data sets. So hopefully we'll get the chance to see examples of skewed data sets. Now we can also get some box plots. We would also like box plots. So go to customizable plots, select box plots, and the color scheme with which JAS provides is quite drab. So we would of course like a good color scheme. Use color palette. Let this run the analysis. It takes a bit of time to reflect the changes. So essentially what a box plot is the solid horizontal line is the median. The box corresponds to, it reflected changes right now. So the box is the lower box margin is the 25th percentile, and the box margin which is above corresponds to the 75th percentile. So here we can see that the treatment group, so the scores are quite higher than the control group. So the central tendency, measure of central tendency here is the median. This is the median, this is the median. So the median is also higher. And we can also get an idea of the dispersion, the interquartile range. So remember what the interquartile range is between the 25th to 75th percentile. So the IQR, you can visualize that this is quite large here, whereas the IQR is quite narrow, it is quite small. So the dispersion in the treatment group is quite lower, and you can confirm that here. So the IQR is 23 and 14 here. So the IQR is smaller in the treatment group. So this is how you numerically explore your data, and here is how you can visually explore your data. So while performing descriptive analyses, it is always highly recommended that you add a mix of both numerical statistics as well as visual statistics. So you won't necessarily include these graphs in your manuscript, but it is very essential for you as a researcher and as a hypothesis tester, as a statistician, to have a very thorough idea of how your data set looks like. Okay, so I think it is enough. It's enough for descriptives. We will run our t-test now. So I'm just closing the descriptives menu because it takes a bit of RAM. My laptop's RAM is not that great. So go to the t-test option. So if you read what is written below t-test, it is evaluate the difference between two means. So that is what we want, right? So if we want to evaluate the difference between treatment group and control group, so the scores between both of these. So go to t-tests. And before running the t-test again, I hope Nafisa has shared my slides on the group. So if you open those slides, there is one slide which corresponds to which test to use for what type of data. So so in that slide, we have what test will you use when your dependent variable is continuous, your independent is categorical, so on and so forth. So t-test, correlation, regression, ANOVA, so forth. So that slide actually contains all the information. And I think she has shared on your group. So if you ever want to go back and check, you can always go there. Or I also have short 3 or 4 minute video on my own YouTube channel. For those who are new, I have my own YouTube channel. So I have actually changed the name. It is now Stat. So I will share my YouTube channel link in the chat box when we finish our session. For now, we'll go to independent samples t-test. So what is the difference between independent samples t-test, paired samples, and one sample? So independent samples t-test is when all of these individuals are different. So individuals in the treatment group are distinct and individuals in the control group are distinct. Okay. Paired sample t-test is when, for example, we want to assess, suppose the same example, the first 21 people act as controls. They have not been trained and their directed reading power test has been measured, and now they have now been trained to read and their scores are again measured, and now we want to see the difference between scores before and after they were given this training. So here the sample is the same, right? So 21 patients, you perform the same intervention on the same group of people. So here your sample is paired, right? So it is paired. They are not independent. So this is when you would want to use the paired samples t-test. But the one sample t-test is when you only have one sample. For example, you for some logistic reason, you cannot procure a control sample. You just have your treatment sample. But in a prior paper, you have documented the scores of a control group. You have documented scores of a control group. Here is when you can use a one sample t-test to compare your mean. You can compare your mean which you got in this study to your mean which you had in a previous study or exists in a previous literature, or a hypothesized control mean. So if you don't understand this, no problem. I will explain this with the help of an example. So for now, we'll perform an independent samples t-test. Go to t-test, go to this independent samples t-test option. Okay. And let me wait. Okay. And now you need to drag and drop these variables similar to what you did in the descriptors. So the DRP will go to the dependent variables box and the group will go to the grouping variable box. Okay. So this is a very basic table which we get, which gives us the t statistic here, the degrees of freedom and the p-value. Now, as I mentioned, there are certain assumptions which need to be met. So what are these assumptions? Go to the show info for this analysis, the I circle here, and you can read the assumptions here. So the dependent variable should be continuous. So this assumption is met. So DRP is a continuous numerical variable. Observations in both groups are a random sample from the population. So assumptions from both groups are random samples. So these are not paired. So the same person has not been, again taken into the treatment group again. So both of these are random samples. The dependent variable is normally distributed in both populations. So here is when the assumption of normality needs to be checked. And the population variances. So variances are homogeneous. So the measure of dispersion in both of these should be, similar. So both of these assumptions can be checked visually or using statistical tests. To make this very simple, I won't go into visual understanding. I'll go into the statistical tests. And you can easily perform both of these assumption checks in this, t-test box itself. So if you scroll down, you will see assumption checks for normality and equality of variances. So if you select both of these, you will get some p-values. Okay, you'll get some tests and you'll get p-values. So if you see here, you will remember this Shapiro-Wilk. It was there in descriptive statistics option as well. So it is the same test. So you can perform the same test in the descriptives, or you can perform this test in the independent samples t-test. So whatever your wish, you can perform the test in either of the two modules. So, okay. Now, how do we interpret p-values for both of these tests? Here, insignificant p-values or p-values more than 0.05 are desirable. Let me repeat. Non-significant p-values more than 0.05 are desirable. If you read this small note here, significant results suggest a deviation from normality. So deviation from normality, that means our assumption is not met. So if we had gotten a p-value of say 0.001, that means that the data is not normally distributed. We confirmed this visually when we saw the distribution curve. So it was quite normal. It was quite symmetric. It was not perfectly symmetric, but in the real world, no data is symmetric, right? So here, the p-value, which is more than 0.05 or a non-significant p-value, suggests that the assumption of normality is met. So this is a good sign for us, all right? Even the p-value here, a non-significant p-value is desirable. So here, even the p-value is 0.13, it is more than 0.05. So the assumption of equality of variances or homogeneity of variance is met. You have two options for equality of variances. So Brown-Forsyth or Levine's. So you can use either of them. There is no problem. So both of these are acceptable. All right, Levine's or Brown-Forsyth. Okay. Now, so all of our assumptions for the t-test are met. We are good to go using the student's t-test. And now we can accept the results of this test. We can accept this p-value because the assumptions have been met. And since the p-value is less than 0.05, that means the difference is statistically significant. So the average reading scores of the treatment group were statistically significantly higher than those of the control group. Okay. Now, we want to get, so we can of course calculate the difference of means by hand. So if we go to descriptives, we can also of course calculate them, but why do that when we can get the mean difference, ready-made for us? So just select the location parameter checkbox, select the confidence interval checkbox. So that will give us a confidence interval for the difference in means. And we get the mean difference with this 95% CI. So approximately 10 points. So that is what we saw, right? So 10-point difference between average mean scores. Now, the 95% confidence interval for the mean difference does not cross 0. So if you remember in my first lecture, I told you when the ratio, the 95% CI for any ratio, odds ratio, risk ratio, hazard ratio, if it crosses 1, that means your result is not statistically significant. If it does not, so if the interval does not contain 1, it means the result is statistically significant. When we have differences, so this is a difference, the interval should not cross 0. So remember 0 for difference and 1 for ratio. So this does not cross 0, right? So minus 18 to minus 1. This does not cross 0. So the result is statistically significant. All right. Now, if you remember in our sample size calculation, we talked about effect size. We talked about Cohen's d. So Cohen's d is also known as the standardized mean difference, SMD, or Cohen's d. And here the Cohen's d, you can, not take into consideration the negative value. You can take the modulus, or the absolute value is 0.68. So it is quite large, right? If you remember from the first session, a Cohen's d of 0.3 was a small effect size, 0.3 to 0.5 was medium, and more than 0.5 was large. So this is almost 0.7, which is of course more than 0.5. So this is a large effect size. So there is a large association between the training, and the effect of training is quite large. So that is how you can interpret Cohen's d. Simply put, you can again get the confidence interval for Cohen's d if you wish. So this will give you a 95% CI. And it is very easy to get descriptive statistics here itself. So you get your mean, standard deviation, standard error, coefficient of variation right here itself. So you can, you don't have to separately go to the descriptors and do it there. You can get it. However, if you note that you cannot get your median or IQR or customized options here. If you go to descriptive plots, you will get your means with the 95% CIs. So this point corresponds to the mean. So this is 42. So 42 and 51. And these are the 95% CIs. So these error bars stand for 95% CIs. Now, rain cloud plots are very pretty and very informative. Rain cloud plots will give you a lot of information in one graph. So this is your jittered raw data. So this is your raw data for each individual score. So one person got 85, one person got 10. So the scores of other people are plotted for control and treatment group separately. These are the box plots. So the same box plots which we saw in the descriptors is the same thing. And even these plots are the same plots which we saw, the distribution plots. So without the histogram, just the frequency distribution density curves. All right. So we can see that the measure of central tendency, the mean for this orange is the treatment group, is larger than the control group. So you can even confirm this visually. So rain cloud plots give you a huge amount of information in one plot. And I think this will be made more apparent when we come to ANOVA. So I think this is enough for a t-test. All right. So what do we do when our assumption for homogeneity of variance, or this Levin's or Brown-Forsyth, so this equality of variance assumption, we get a significant p-value. That means our assumption for the variance assumption is not met. So we will perform the Welch t-test. So if we get a significant p-value, do not worry, just select the Welch option and you will get a Welch t-test. So we use the Welch t-test option if your equality of variance assumption is not met. All right. So remember, V for variance, so V and W, so they go hand in hand, V and W.
Oh.
All right. And what do we do if our assumption of normality is not met? That means that remember, what do we mean by not meeting these assumptions? The p-value should be significant, less than 0.05. So here we only have one p-value, so there is not a problem. So if the p-value is less than 0.05, use the Welch t-test. In this Shapiro test, if any of these p-values is significant, so for example, say that the control group p-value is 0.01 and the treatment group p-value is, let it be 0.65. So even if one of the p-values is significant, you would still want to use a non-parametric test. So in this case, a Mann-Whitney test. All right. So if any one of these is significant, you will straight away use the Mann-Whitney test. If both of these are significant, of course, you will still use the Mann-Whitney test. There is a very interesting thing to note here, a very important thing. So if you remember, we saw how we calculate sample sizes for a t-test, right, in the very first session. So we calculated our sample size for running a t-test using some standard deviation. We used some effect size, we used some power, we used an alpha error, right? So if you remember that, we calculated sample size. Before performing your research, before performing your study, if you had calculated a sample size, and if this test of normality, you get a significant p-value, it is still okay to use your student's t-test. It is still okay to use your student's or Wells t-test, depending upon the Shapiro-Wilk test significance. So that does not matter if you had calculated your sample size properly before running your study. This is important. Okay, so suppose that you haven't calculated your sample size formally and you have a significant p-value. Then you would not test for your difference in means, but rather you would want to test for difference in distribution. So the Mann-Whitney test, you can select this checkbox. So the Mann-Whitney test is a test for difference in distributions. So remember that it is important to note that many people think Mann-Whitney test, also known as the Wilcoxon rank sum test. So both of these are synonyms, so Wilcoxon rank sum and Mann-Whitney. So many people think that using the Mann-Whitney test is a test for medians. So no, it is not a test for medians. It is a test to check for differences in distribution. There is a separate test to check the difference in medians. It is called the Moore's median test, but that is not the subject for discussion in this lecture. So the Mann-Whitney test is a test for difference in distribution. So if your p-value is significant here, you would use the Mann-Whitney test. And so even the Mann-Whitney test p-value is significant. So 0.01 is significant. And you see that the distributions on both of these curves are different, right? So both of these curves are not completely overlapping, right? There is some non-overlap. So, you see this green curve, there is non-overlap, right? So can visually understand the difference, the significant p-value here by visualizing. So I think I will stop my parametric and non-parametric t-test, and I will now go to ANOVA. It is already 6:10, it is 1 hour. I will quickly explain ANOVA in the next 10 minutes, 15 minutes, and then I will yeah. So could you repeat on how to interpret Mann-Whitney values? Okay. So, the W statistic is the Mann-Whitney W statistic. So do not concern yourself with the W statistic. You just see the p-value. Okay. The p-value is significant. That means that there is significant difference in distribution of both of these curves. So both of these curves, there's a difference in the distribution of values. So for the control group, more values, there are a lot more smaller test values, the DRP values. And for the treatment group, there are a lot more higher values for the DRP. So that is reflected by these distribution curves. So the orange distribution curve, you see it is, a little more, it is above the green distribution curve for the control group. So that is how you can interpret visually. Now, if you are asking for what these Hodges-Lehmann estimate and what the rank biaxial correlation is, I can try to explain, but I won't guarantee that you will understand. So the Hodges-Lehmann estimate is simply put, crudely put, it is a difference in medians. It is a difference in medians. It is not actually a difference in medians, but we can interpret this in crudely a difference in medians manner. Okay, so you can say that the difference between, so the Hodges-Lehmann estimate was 10. That means that there is a difference of 10. So a score difference of 10. So that is how you can interpret this value. The 95% CI should not cross 0. Again, that is take into consideration that if your test is significant. The rank biserial correlation, I haven't dealt with correlation analyses up till now, but this is essentially your correlation coefficient, simply put. So your bivariate correlation coefficient. So when we come to correlation, when we talk about Pearson's correlation, when we talk about correlation coefficient R, right? If you remember R from your statistics lectures, your correlation coefficient R. So this is exactly the same correlation coefficient. So even these are segregated. So if I'm not mistaken, a rank biserial correlation of 0.1 is small, 0.3 is medium, and 0.5 is large. So this is medium to large correlation coefficient. Of course, don't take into consideration this negative value. Just for the sake of simplicity, take the modulus or absolute value, 0.44. So a medium to large correlation coefficient. So that is, how to interpret. So I think, is it okay? How does this correlate to the hypothesis? So our hypothesis was for the t-test. So there's a difference in the means, right? If we want to formulate a hypothesis, a non-parametric hypothesis, we would hypothesize that there is a significant difference in the distributions of these scores. So that would be our formal alternative hypothesis for a Mann-Whitney test or a non-parametric test, right? So the null hypothesis will be there is no difference in the distribution of scores between the control group and the treatment group. And the alternative hypothesis will be there's a difference between the distribution of scores between both of these groups. So a significant p-value, we would accept the alternative hypothesis and we would say that yes, there is a significant difference in distribution between both of these groups. And by looking at these box plots or these curves, we can say that the distribution of the treatment group was significantly higher than the distribution of control group. So that would mean that the scores in the treatment group were higher than the control group. So that is how you would interpret or correlate your hypothesis with this test. So let me move on to ANOVA now. I would get a little more chance to explain when I ask you all to perform these tests yourself. Now I want all of you to go to show main menu. Okay, show main menu, go to open, go to data library, go to ANOVA, and let me see which one do we want to use. Okay, let's take a fun data set. Beer goggles. Open the JASP file for beer goggles. Go to this show main menu, open data library, ANOVA folder, and the beer goggles JASP file. So I want all of you to go to the data viewer, right? Just have a look at the data before reading the description. So this data set gives us 3 variables, it seems. So face type, alcohol, and attractiveness. So attractiveness looks like some sort of score. Alcohol and face type looks like some sort of quantity or nominal variable. So let's see what this data is. Okay. So this data set, beer goggles, provides attractiveness ratings, so median attractiveness ratings of 50 attractive or unattractive faces after consuming different amounts of alcohol. So this is an interesting data set. So I'm sorry if anyone is offended by this alcoholic data set, but I think this data set is hilarious. Again, no offense to any sort of group, anyway. So face type. So this is the attractiveness of the rated faces. So 0 means unattractive and 1 means an attractive face. Alcohol is the amount of alcohol consumed. So 0 is a group which corresponds to 500 ml of non-alcoholic beer. 1 is the low dose group, so low dose of alcohol, right? Low dose is 500 ml of average strength beer, and 2 is the high dose group, so strong beer, 7% beer, so 500 ml. Okay, so to reiterate, 0 is placebo, 1 is low dose, and 2 is high dose, okay, of beer. And attractiveness is the median of 50 attractiveness rating. So it is a bit complex to understand. It might be a bit complex to understand. So there is there is one person, and he has been randomized to 3 groups. So either placebo, low dose alcohol, or high dose alcohol. Okay, and then this person is shown 50 people. Okay, this person is shown 50 people, and he is now rating them on an attractiveness scale. And if you see this description 0, so 0 is non-attractive, or pass me a paper bag. Okay, and 10 is pass me their phone number, so very attractive. Okay, so from least to highest. And now they have rated these faces on attractiveness ratings. So 3 groups. So placebo, low dose, high dose, and 50 people they have been asked to rate, and the median of their 50 scores have been noted. So these are the median scores. Okay. So now we want to test our. So for this example, we will forget about face type. So don't face type, forget about this. Just focus on alcohol and attractiveness ratings. So let's formulate our null hypothesis. Our null hypothesis will be there is no difference. Okay. Does anybody want to try? Let me ask someone to try. Abid Pal, do you want to try formulating the null hypothesis? Can you unmute and formulate? Okay, next. Toin Dairo, do you want to try?
I can try. Did you want the hypothesis or the null hypothesis?
The null hypothesis, please.
Okay.
So let me formulate the research question first. We want to test whether there is a different amounts, so different doses of alcohol. So placebo, low dose, or high dose, whether they make a difference, whether they make people perceive people as more attractive or less attractive. So that is what we want to test. So now I wanted to formulate a null hypothesis for this.
So I think the null hypothesis would be that the amount of alcohol that one consumes does not, how do I say this? Does not
Make any difference.
change the perception of attractiveness.
Yeah.
Yes.
Okay. That is well put. That is well put. So essentially, there is no difference in attractiveness ratings of people who have been given the 3 amounts of alcohol. So that is how we formulated the null hypothesis, and that was perfect. So what you mentioned was perfect. So that is how we can formulate. And of course, our two-tailed alternative hypothesis will be there is a difference. Okay, there is a difference. We don't want to say whether there's a difference, whether low dose is better or high dose is better. We won't say that. Is a node? Yes. Yeah. So we don't want to say that there is a difference and it is tending towards any one side. We just say that there is a difference between these 3 groups. Okay, so to perform, so if you go to that slide which I talked about, so what type of test do we use for what type of data, you would see that when your dependent variable is continuous or numerical and your independent variable is nominal or categorical with more than 2 groups. So more than 2 means more than or equal to 3 groups. You would want to use your analysis of variance. So here we have 3 groups, right? 0, 1, and 2. So 0 is placebo, 1 is low dose, 2 is high dose. There are 3 groups. So we can't use our t-test, right? If we wanted to use our t-test, we would have to separately do it for 0 and 1, 0 and 2, and then 1 and 2, right? But we want to test your entire hypothesis at one go. So don't forget these pairwise tests, okay? Because those will come into handy when we perform what are known as post hoc tests, okay? So pairwise comparisons will be t-test 0 and 1, 0 and 2, and 1 and 2, right? So don't forget this for now. We will come back to this later. But now we want to perform an ANOVA. To do that, go to this ANOVA module. You can read what it says, evaluate the difference between multiple means. Go here, go to ANOVA underneath the classical statistics option. Oh, let me just remove the first analysis, which was ready-made for us. And while I wait for the initialization of this module, you can open your module in your own computers. It is now loaded. So we can put our dependent variable, our continuous dependent variable, into the dependent variables box. I've told you to forget about phase type. So, just don't look at this. Look at alcohol. Alcohol is our grouping variable. Okay. Your grouping variable should go into the fixed factors box. And now let's run the ANOVA. Because, so here we get our p-value, there's a significant p-value. That means we reject our null hypothesis. So significant p-value less than or equal to 0.05. This is 0.03. So we reject the null hypothesis and accept our alternative hypothesis. To, test whether these results are valid, we would of course like to check whether the assumptions for ANOVA are met. So go to show info for this analysis, okay, and check the assumptions. So residuals are normally distributed for every group. So residuals are a concept which need to be taught visually. I won't go into this. I won't go into this right now. Independent variables are categorical. Dependent is continuous. So this is met, right? So the dependent is continuous, that is met. The independent variable is categorical, that is also met. The variance for the dependent variable is the same for every group. So again, if you remember, we tested for homogeneity or equality of variances in t-test, and we will do this again. So in t-test, we use the Brown-Forsyth test or the Levine's test. We'll use the same here. And the groups are independent. So yes, the groups are independent. So the same people haven't been put into the three groups of alcohol. So these are separate people. All right. So remember that we would like to test for the third assumption and the first assumption. So normality of residuals, right? And homogeneity of variance. So these two assumptions need to be met. So how do we do that? Scroll down, go to assumption checks, and here we get our homogeneity test. So run this Levine's assumption check, and so Vidhi Vora, would you like to interpret the result for this test? The p-value? Pratik, would you like to interpret this?
The p-value, if you are assuming a 95% correlation, then it is not statistically significant. So this will be the assumption for normality is, I mean, it is a normal distribution.
No,
sorry. I mean, we can assume that there's an equality of variance. Is that right?
Yes, yes. So this is non-significant, right?
Right.
Yes. Okay. So the assumption is met, correct?
Yes.
Okay, great. Perfect. That's true. Okay, Vidhi's mic was not working. No problem, Vidhi. It's okay. Now, the first assumption, the residuals are normally distributed. So how do we test that? So JASP gives us an opportunity to test this visually. So select this QQ plot of residuals option, which will give us QQ plots. Okay, it's fun to say QQ plots. We get QQ plots, and so these are quantile plots essentially. And what we want to check visually is that all of these data points, especially in the center, follow this straight line, and the dispersion is not that high. So this is what we want to visually check. And this is a great example that the assumption of normality is met. So the data is normally distributed. Because if we see, all of these values are quite close to each other, and they follow this line perfectly, this line. At the very, so these are known as outliers, right? So the extreme values. So these values, they have thoda sa deviation hai inme. There's a little deviation, but that shouldn't be a problem, right? Outliers usually pose such a problem, but that is not. The main thing which we want to see is that these central values should be quite close to one another, and they should follow this line. And this is a very good example that yes, so data is normally distributed. So this is a sigh of relief. That is good. Now, okay, let me, for grin's sake, let me show you. So we can test for normal distribution. So where is the point? There's no, yeah, okay. So there is no definite point. So these values would be very scattered. Okay, so around this line, the data would be very scattered, or these outliers would be very spread apart. So I hope you can see my mouse cursor, right? Can you see my mouse cursor, Nafisa?
Yeah, I can see that.
Yeah. Okay. So if these values were to be, say, spread here, then it would be non-normal. Or these values, so one value here, here. So very far apart, then we would say data is non-normally distributed.
Non-normally distributed.
distributed. The residuals are not
Oh,
normally.
it's not
So,
subjective.
yes.
Uh,
Yes, it is subjective to a certain extent. It is subjective, and so there are statistical papers which argue that visual checks for assumptions are sometimes better, because if you rigidly follow statistical tests, so consider this test, if you rigidly follow that, for example, now what if the p-value was 0.045? It is very close to 0.05, right? So sometimes this can be misleading, and you would rigidly follow that. Oh, the data is non-normally distributed, let me follow a non-parametric test, let me go for a non-parametric test. So no, it is so people are arguing that instead of you rigidly following significance for Levin's test, say, or Shapiro's test, visual representation or subjective visualization of data is better. But the caveat here is that subjective assessment should only be done by experienced people, experienced statisticians, because novices might not recognize okay, so where exactly would we draw the line between non-normality and normality? So like Pratik rightly pointed out, so where is the exact point? So there is no point as such, but it is more of a subjective experience. So yeah, this data is normal, this data is not normal. So here is when your subjective experience will come into play. So both good points that Pratik has raised, and thanks for the questions from day one. He's raising the correct questions, so he gives me a chance to explain. So thanks, Pratik, and I hope this is clear now. Okay, great. So residuals are normally distributed, equality variance is met. Let me just uncheck both of these so that we get a clean analysis output here. Okay, so what will we do if our assumption of homogeneity was not met? So here, just below this assumption test, Nafisa, can you I think there is some interference from your side.
My side?
Yeah. Okay, thanks. Sorry for that. There was some interference. So in homogeneity correction, in homogeneity correction, you can use the Brown-Forsyth test or the Welch test. So if your homogeneity test, so if that was violated, then so if your p-value is significant, then you can use either a Brown-Forsyth correction or a Welch correction. So either of the two are fine. You can use either of the two. Okay, and let me give an example. So this is how your test would look like. So Brown-Forsyth homogeneity correction, and then your p-value, and so it looks the same, but you just haven't applied a correction. And what would we do if our assumption of normality of residuals was not met? We would use a non-parametric test. So if you see this last option, non-parametric, it is there for a Kruskal-Wallis test, but I will explain that afterwards. Okay. All right. Very conveniently, JASP has given us an option to get descriptive statistics right here itself. So, because I wanted to, run through ANOVA because it is already 6:30, I did not perform a descriptive analysis. So here we can see our descriptive statistics itself. Okay, so the mean attractiveness rating increased, right? So these are groups. So group 0 is placebo, 1 is low dose, 2 is high dose, and this is the mean for attractiveness rating. So these have increased. So those who were given placebos, the average attractiveness ratings was 5. Those who were given 500 ml of 4% strength alcohol, the attractiveness rating was 5.7 on average. And those who were given 500 ml of strong beer, 7% beer, their attractiveness ratings was 6.4. So higher, higher, and highest. Low, high, and highest, sorry. All right. And the dispersion is, quite similar. Okay. So that's fine. Now, we can also get estimates of effect size. So eta squared, partial eta squared, or omega squared. So I won't go into this right now. I would now. So, okay, let me interpret the p-value for ANOVA. So the p-value is significant. The p-value is 0.03. That means we reject our null hypothesis and we accept the alternative hypothesis. So what was our alternative hypothesis? There is a significant difference between the mean attractiveness ratings between these three groups. So that was our alternative hypothesis. And we accept that. But where is the significant difference present? So is it between 0 and 1? Is it between 1 and 2? Or is it between 0 and 2? So here we can now perform pairwise t-tests between all of these groups very conveniently using the post hoc tests drop-down menu. So just select the alcohol, put it into the alcohol into this box here. Correction, I won't go into p-value correction here. You can also get some confidence intervals and you can flag significant comparison. So, all right. So here, the significant difference lies between 0 and 2. So the post hoc test suggests that light beer did not make a difference, but strong beer did, right? So there is a significant difference between placebo versus strong beer. So when you drink strong beer, you are significantly more likely to rate people as more attractive. So that is how you interpret post hoc tests. And in descriptive plots, same. It's the same plots which we saw in the t-test. So mean with 95% confidence intervals. It's taking some time to load. And raincoat plots are the same. So while this loads, you can take this time to run the test yourself. And you can confirm check what the post hoc comparisons mean. Okay, we got our descriptive plot. And make this bigger. And we can see that the average attractiveness increased. So this is how it increased between 0, 1, and 2. And we can see that the attractiveness rating distributions are also different. So the violet one is for strong beer, the orange one is for light beer, and green is for placebo. So you can see that these are non-overlapping, and placebo is lowest. In the middle, you have light beer, and here you have strong beer. So these are distribution curves. These are the box plots, and these are the raw data points. Now, let me explain the non-parametric test in brief. So you will use this when your assumption of normality of residuals is not met. So just select the alcohol variable and put it into this box. And it will perform the Kruskal-Wallis H test, which is the non-parametric test for distribution. And I'm not sure, there used to be post hoc tests for the non-parametric as well, but I am not sure where they are, but I think it's fine. You can use this post hoc comparisons for Kruskal-Wallis test itself. So this test is used when your normality of residuals is not met. An important thing to note about non-parametric tests. So this is an interesting concept. I hope you all understand this as I explain. The thing to note is I had explained what power means, right? So power is the ability to, so it is 1 minus a type 2 error probability. So type 2 error is when you accept false negatives, if you remember. So so do you remember? So power is your ability to actually see a difference when one exists. False negative is when in reality a difference exists. A difference exists, but you are not able to quantify. You are not able, in your test is not able to prove that there is a significant difference. That is what we mean by false negative, right? False negative. So it is a false negative. So your power is the ability to, is 1 minus false negative probability. So non-parametric tests, interesting to note, non-parametric tests have lower power to detect a difference than parametric tests. The Kruskal-Wallis test is a non-parametric alternative to the parametric ANOVA. Okay, I think we can conclude in the next 10 minutes because I think people would like to share their screen. So I think, would you like to share your screen and do some examples yourself? So I think last time Saurabh and Pratik shared the screens. Today, Vidhi, would you like to share your screen? But I think her mic is not working. Okay, let's see how we can manage that, or perhaps next time. So just to conclude, non-parametric tests have lower power to detect. So they, more false negatives are seen when you use non-parametric tests. And this is what we see here. The p-value is not significant, but your parametric p-value is significant. It was 0.03. So this is a false negative, right? There is a significant difference, but it has not been able to detect it. So non-parametric has this downside. Just remember this. Okay, I think I'll conclude my screen sharing. I'll stop my screen sharing. And is there a difference in the interpretation of ANOVA after applying? No, there is no difference. When you correct with Brown-Forsyth or Levin's correction, there is no difference. You interpret in the same way. For the Kruskal-Wallis, you interpret that there is a difference in distributions, right? There is a difference in distributions, not means. And ANOVA is for means. Okay, Vidhi, would you like to share your screen? Because last time Kumar and Pratik both had shared the screens, but if Vidhi cannot share her screen, we can ask. I don't know. I think we only have time for either Kumar or Pratik to share the screen. So if Vidhi share her screen, it's good. Otherwise, I don't know who wants to
I can share my screen, but the thing is that I am.
Yeah, of course, please. I'm sorry, I did not. Yeah.
No, don't. Not. No, what I'm saying is that it would be difficult. What could you see? I would have to do like that because I'm being joined from my phone and running on it on my.
Sure,
laptop.
great, no problem.
Chalo, let's try.
Okay, I want you to go, show main menu. open data library, ANOVA, and let's see. No, not beer goggles. Beer goggles we have already done. Go thoda down. Let's see what data sets we have.
Facebook friends.
No, not Facebook. Yeah, but let's see. Facebook friends or
Heart rate.
no, that's a look for a one-way ANOVA. Is there any one-way ANOVA?
Ooh, 10
example. Yeah, pain
next to
thresholds.
this-
That's fine. Pain thresholds. Pain thresholds. Pain thresholds. Open the data file, not a JASP file. I'll explain. I know this data set. You opened a JASP file, but that's okay.
Okay, let me change the data file.
Yeah. Till then, I'll answer Pratik's question. Is there just to see if I understood correctly? There is a high chance of getting false negative. Yes. Yes. Not a high chance, but a higher chance relative to ANOVA.
Pain threshold.
Okay.
I love that it is able to work on a multiple files at once, right?
Yes, it is. It slows your, if you have a smaller RAM, then it slows your analysis down. But if you have a good RAM, then okay. So I'll explain this data set. Let me explain this data set. It is another funny data set, and again, no offense to anyone. Please do not take offense. These are just meant as fun data sets. So here we want to find out whether there is a people. We have recruited people. We have recruited light blondes, dark blondes, light brunettes, and dark brunettes. So we have recruited people according to their hair color. Okay, light blondes, light brunette, dark brunette. We want to test whether there is a difference in pain thresholds between these 4 groups. Okay, so we want to check whether there's a difference in pain thresholds. So Nafiza, would you like to share your null hypothesis?
My null hypothesis is that there is no difference in the pain threshold of all the groups.
Great. Okay, perfect. So I want you to first perform descriptive analysis on this.
Okay, so hair color, pain tolerance is the variable.
Yeah.
And hair color would be the split.
Perfect. Okay, so what do we see here? Dark brunettes. Oh, their pain threshold was quite low. Okay.
Yeah.
Standard deviation are, pretty similar, but we'll test that with the Brown Forsyth test later on, the dispersion.
So
would you
the
like to get some
you can
box
say
plots?
you can dispersion you can check. Okay, no. Okay, all right.
Yeah.
Range is there. Okay, then do we need some plots?
Yes. What plots would you like to generate?
I would like to generate distribution plot.
What about
QQ plot?
density curve?
Display density.
Yeah.
So I think it has for different hair colors: dark blonde, brunette, light, and dark blonde and brunette.
Yeah.
So you can see in the pain tolerance in the dark blonde, it's not a normal distribution curve, right?
Yeah. So, yeah. So I think this is fine. Perhaps the assumption of normality might be violated, but let's see later on, because these distribution curves So, okay, this is a good example of positively skewed. So if you can go a little bit up the first distribution graph. Yeah, this is a positively skewed data set because, so forget about the curve. Just look at the histogram bars.
One is very long.
So
and
there
others
is
are
steep
equal.
increase from 40 to 45, and then there is a gradual, decrease in slope. So this looks like a positively skewed distribution. If you go to second or third graph, it is also positively skewed. Yeah, this graph again positively skewed. The third graph is fine. It is not skewed.
Normal. And
Yeah.
also the distribution curve is also
Yeah,
right.
it's fine. This is also probably normal. Okay, one thing, Nafisa, could you direct your camera to the middle pane? If you see this rug marks, no, yeah, and you can select probably no. I wanted to go to the bin type width type and go to bin width type. Go to manual and let's see. Yeah, okay, great. So now you can change the distribution characteristics. So for every you can see that the so between 50 and 60 it has further been divided into I guess 5 separate
Yes, 1, 2, 3, 4, 5.
data points. Yeah,
But it
so you can
is
see
different. Like here, it is like here it is in 2. It's here it's in 5.
Yeah, it is totally different because we have from the least to the largest, we have divided that by 30. So if you go to the options, it's 30. You can see that.
It is 30.
Yeah, that is why. Okay. So would you like to generate some box plots?
Yeah, sure. Where did my basic and customizable plots?
Yes.
Box plots with the color bar. Why are they not showing?
Have you selected box plots?
Yes. Okay. Wait. I have. I opened a new window now, so I think it. Okay, so these are the box plots.
Yeah. So visually we can see that dark brunettes and light brunettes. So brunettes had lower pain tolerance than blondes. So blondes had a larger pain tolerance. So now we would like to test this hypothesis. So can you perform an analysis of variance ANOVA for me?
I have to start the ANOVA, right?
Yeah.
Okay. So here is the fixed factor, and the pain tolerance is the dependent variable. And what is this WLS weights?
So that is when you want to perform a weighted ANOVA. So if you have weighted variable, so that is a complex topic. Yeah, assumption checks. So before running that, can we see the ANOVA p-value? What is the p-value? Is it significant or not?
It is significant, less than 0.0.
Okay. Let's see whether we have met our assumptions.
Okay, homogeneity test. The p-value is not significant.
Okay, good. That's good.
Should we apply some correction, but it's not significant?
No, it's not significant. It's fine. No need to correct.
See, our data is also almost normally distributed.
Great. That's fine. This is good. No problem. In distribution normality, that assumption has also been met.
Yes. Then do you want
It is not grossly. This is fine. Yeah.
Okay.
Okay. So now we can accept the results of our ANOVA that it is statistically significant. We can reject our null hypothesis. And now I would like you to perform some post hoc tests to see where the statistically significant differences lie.
Okay.
You can check the flag comparisons checkbox also. So that will make it easier to see.
Okay.
Yeah. So the two stars, right? So
You're able to follow my screen, right? No? Because
yeah, it's fine. So this dark brunette versus light blonde and light blonde versus light brunette. So the 4th and 6th are significant. So if you see the p-values, they are 0.037 and 0.004. So these are significant p-values.
yes.
So there is a difference between these pairwise groups. So there is a difference between pain thresholds between dark and light blonde, dark brunettes and light blondes, and dark blondes versus light brunettes. So there is a difference between these groups.
Yes. Okay. Okay. Tell me, what are these corrections?
So these are so there is something called multiple comparisons. Okay. So here we have performed pairwise comparisons, right? So for so many groups. Now, when we perform so many pairwise comparisons, there's a concept called as alpha inflation. So alpha error is the type 1 error rate. So type 1 error rate is false positives. So when we
false positive.
Yeah. So when we perform so many pairwise tests on the same small data set, there is a chance to get false positives. So
Okay.
false positives, not true positives. There is a chance we'll get false positives. To reduce the rate of getting false positives, we apply what are known as multiplicity comparison kit tests. So these include the Bonferroni correction, home correction, Sadak correction, Tukey's correction, etc., etc. So the most commonly used are Tukey, Bonferroni, home, and Sadak. All right, and out of all of these, the Tukey correction is the least conservative. So
Okay.
you would like to use the Tukey's most of the times.
Okay.
So that is the essence of p-value. So your p-value is correct, and you would find sometimes that when you submit a manuscript, when you perform so many tests and you do not correct your p-values, reviewers will oftentimes comment that where is your p-value correction and why haven't you corrected for so many comparisons? So you would need to answer that, and you would probably need to correct your p-values for multiple comparisons. So essentially, yes, so this is what is our p-value correction method.
Okay.
And I think we can stop now. It's been 2 hours.
Yes.
And
So,
yeah, plots. Yeah.
I'll make one brain cloud plot. Also. I think this is the one.
Yeah.
So we have
So-
already seen the distribution, the bar box, the box one, and this the normal distribution one.
Yes.
Okay.
So
Here you can see that in the which one is blue?
dark brunette, light blonde, and dark blonde, light brunette. So there is a difference between all of these.
Yes, someone has higher. This one is dark brunette.
So I think those who have darker hair colors have more this thing, higher pain tolerance.
That makes sense. Indians have the darkest hair since we have a pretty good
Yeah.
paint tolerance. Okay. So I guess should I close the?
Yeah, you can stop your camera. And I think, thank you everyone for attending this session. Next session will be focused on, yeah. So Vidhi, I will hold you to your word. I would want you to volunteer next time. And Emmanuel, next time I want you to volunteer as well. Saurabh has been given ample opportunities to volunteer.
I will do my best to volunteer the next time. Sorry, I came in late.
Oh my
and I
God!
had-
How late are you? You should have been loud in this session.
Now, first of all, I just got back from church. That's why I got back like really late. But yeah, next time I'm definitely volunteering. I and VD, we are volunteering next time, definitely.
Yes, that's good. And all right. Stack Potato, do you have something to say?
Yeah. No, it was
That-
awesome, and it was an awesome session and really informative. But a bit of it was a bit difficult for me to get today. I'll review it if I could get the recording once more, because the last part, especially the interpretation of some things, Carrie Willis and the Levine, something which you told, the interpretations of those things related to the ANOVA plot, those were a bit new concepts which I heard today, and I need to review them.
Yes.
That's from my purpose.
Yeah. And before I go, let me share my, because I think you have my YouTube channel link, but for I don't know if everybody has, but you can check out my ANOVA playlist in my YouTube channel. And I think I don't remember which data set it was, but
if it's available as a tutorial in YouTube, to काफी help हो जाएगा. I will take that.
yeah. And of course, now see, the thing is, these sessions recordings, because this is a very informative, informal session,
Exactly.
it needs to be edited thoda. So these sessions need to be edited before we make it publicly available, because now see, our conversation right now, it might not be very nice to put all of this in a tutorial, so to speak. So
Exactly.
we'll edit that, but till that time, you can always go to my channel and see my tutorials on my channel, in my channel.
Okay. Thanks for the great favor. That's all I need.
I love your new channel name, Stat.
Yeah.
I love ordering all the stat medication. Okay. And
Yeah.
Sudhup, I wanted to talk to you about something else too. We'll just connect for a minute after this session is concluded.
Yeah.
Any doubts remain for you all?
No, sure.
So you can ask if ever. Okay.
It was more than enough. Thank you and bye-bye.
Okay. Thank you, guys.
Bye.
See you. Bye.
Bye-bye. So I was asking that for the next two sessions, have you figured out a way to take international payments, or what we can do is we see how many people attend and then I pay you for all of them, because it's 50 rupees is just too less an amount, right?
Yeah.
To be collected internationally, you'll lose so much in the transaction itself.
So I think what we can do is perhaps for Indian citizens we can keep it 50 rupees, and for international citizens perhaps we can keep it $3 or $4, something like that, USD.
I was gonna say $10. I even told you last night, but he mentioned in the PDF. So now it would look rude that they suddenly raise price for us international people.
Yeah.
So that would look rude, but I was saying, but that is okay. I think for the later on, you can take on one-on-one mentoring and then charge them.
Yes.
Internationally.
Yes. So I think it would be better if we get a centralized payment from you. So that would be
Yeah, because it is like even useless for me to collect $50, 50 rupees internationally, right?
Yeah.
And I told you the 2 fiascos that I did while collecting membership fees. So that is why I was asking that whether you guys like find a way, because you will have good clientele.
Yeah. Let me ask Yash and get back to you. Let me ask Yash.
Yeah. Let's see. I mean, figure it out for long term. If it is there, well and good. If not, also then it's okay, fine. The centralized option is already on the table. So I will not mention it on the group because I have had. I'll just let them know that the it is paid and you registered your interest.
Yeah. We will.
Yeah. Okay. So next Saturday, Sunday, 5 p.m.
Yes.
Yeah.
Yes.
Okay, and these sessions have been so helpful and even very interesting, no? Because it's been hands-on. I was gonna sleep. If it was theoretical. Stats they don't come to you naturally. No, you have to use your brain continuously.
Yeah.
Cognitive effort required is very large.
Yeah.
And the more simple they make, the harder it gets, because the concepts are not repeated, right?
Yes. No.
So yeah, but again, thank you for doing this with everyone, and you're always welcome in all the community events in Innores. And even if it's if you would like to take part as our in-house stat advisor also, then also I'd like to welcome you with that.
Yeah, that would be great, because I mean, RQS and Innores will have a
collaboration. Yes,
collaboration.
I already signed up. Yeah, I was asking you that you needed some funding. So if you join us as an advisor, we could sponsor some kind of software or anything that is required, I was gonna say. So, because that would be useful.
Yeah, mainly right now our funding needs are more of logistic purposes, paying PR teams, CACS, stuff like that, maintaining the website, website design, and stuff like that.
Yeah, I got that idea, because even running an organization, so I have already had such trouble. And yours is a for-profit venture, so you would have to take extra care of the accountability and everything. No accounts, you have to get it done every year as well.
Yeah, yeah.
So that is why I got so many offers, no, even for CSR, for Innores and everything. They're like, "Hey, you registered it at a Section 8 company and whatnot." And I'm like, please, I don't have time to get into that puddle.
Yeah.
It's very, but it is for you, it is good because in long term you would be able to generate a good amount of revenue from this.
Yes, that is what we hope.
No, it is very easy, and you don't even need a PR team or anything like that. All you need is to just reach out to organizations like us, and even not that, you reach out to the PG people because they are. I sent you one. Did she contact you?
No, she did not contact us.
She recently made a senior resident. No, her life is hell, but she will
Oh.
contact you. Her thesis guide is pestering her to publish her master thesis.
Yeah,
So
we are ready and we are excited to work with her. So yeah.
So like you reach out to people like PGs, and in once she was I was telling her about your workshop, and she was like, if I like it, my friends were also hunting. Like she paid so much last time to somebody, and they did nothing on her. Like
Yeah,
they did nothing.
that is very sad, and it is, I think, prevalent everywhere. Statisticians take an ungodly amount of money, 5,000, 10,000, 50,000, and they just perform chi-square test and give it. So I mean, it is just frustrating for the clients and even the guides, these papers do not get published in good journals, right? So
वही तो, अरे वो उसके लिए भी पैसे देने पड़ते हैं। ये गुजरात के बच्चों ने या पता नहीं किसने एक जर्नल खोल रखा है, 7,000-8,000 में वो पब्लिश करके देते हैं। सिर्फ थीसिस पब्लिश के लिए कर रखा है, क्योंकि बाकी कई जगह होती ही नहीं पब्लिश। It is very मतलब वो उसको पूरा धंधा ही बना रखा है। But again, if you are providing quality services, and I told you the prices are like super cool, you use these prices for a year to form a strong clientele and then gradually increase. Because PGs do have higher paying power, but as I told you, they have bad experiences. So, and plus yours is a newer firm, no? So just take a little bit of time and post the testimonials, like whatever projects you do, ask them for a detailed feedback, and just post it on that. Like that's what I have done, right? So yeah.
Correct.
So good talking to you, Sudup, and let's meet again next. And centralized one is done. And if you find a way to take international payments, just let me know.
Yeah, I will. I'll talk with Yash and let you know.
Okay. Chalo. Bye.
Yes. Okay. Bye. See you.
Okay.